So I'm live. Okay, good morning, dear students. Today we have the last lecture of the course called Information Retrieval. And this will be the lecture which is not as usual as it was previously. So today we don't have slides. Today I'll be using whiteboard. We will benefit from the fact that this lecture room doesn't have curtains. So anyway, the whiteboard will be more visible than the slides during the daylight. And today I will cover a topic which is, for some reason, not covered in the book, and for some reason is not usually discussed today. Maybe because it is considered outdated, because like 20 years passed, or maybe because it's not in the paradigm of today's information retrieval. So you remember that for the last semester, we discussed very straightforward approach. So first, we stopped on the concept of information retrieval. What is this? This is a satisfaction of information need of a user. Yeah, so the user needs information. User goes to a system and exploits a system to get the information. And then we define the concept of relevance. What is relevance? Relevance is whether the user gets what he or she needs. Yeah, the user goes to a system, wants something, and the result of the system satisfies a need. So this is called relevance. Relevance is a subjective measure. Nice. Next thing is that you remember in the very maybe first lecture or the second lecture, we discussed that there are two major models. One model is that there are documents which satisfy the condition and documents that not. It's a binary retrieval. Yeah. So when you have a word, you want to see all the documents which contain this word. If documents doesn't contain this word, they are not in the set. Exploring such situation is a hard thing because the collection is growing, and today the set which contains the word, for example, can be enormously big. Yeah, and if you show like millions of documents to a user without any order, user will be not satisfied. Other thing is to introduce the probability relevance model. So when you say that we will show the documents in the order, which maximize the probability of relevance in the top and goes down. Yeah, so the most probably relevant document will be the first in the ranking. That's how the ranking appears. That's how we said that the document should be ordered, not just a set, but it should be an ordered collection. And user will scroll down as long as information need is not satisfied. Yeah, so you want to see something. And then we did what? We made few steps towards how to introduce such ranking. And you remember that the cornerstone idea of the ranking, at least for the half of the course, was to somehow find a latent space, vector space usually, which includes all the documents and tries to approximate relevance with some metric. Yeah, so the documents should be more relevant, so the query and the document should together be more relevant to each other if there is a small distance in the metric space. Okay, so we based our assumption about this on content of the documents. And this was the general idea. Yes, of course, later when we spoke about the quality, we talk about that, yes, sometimes users need something else. For example, users need freshness. Users need to see fresh documents rather than old ones. Users need novelty. The users need the documents which were unseen by them. So the next iteration of, and when you like pull the Facebook, how you call it, ribbon, or yeah, bless you, Facebook feed, it should update and show on the top the post you never seen before. And that's the idea of novelty for you. And some other properties of data, which you see, which can improve the satisfaction of a user in terms of information need, because the new information should appear. But maybe you remember we spoke about recommender systems, or maybe you covered this in the other course, that there are two major approaches to building recommender systems. One approach is called content-based, And this is what we actually discussed. So we have a content of the document, and we try to use like text representation or image representation to somehow encode it into a latent space, and then build a ranking. The other approach is behavioral. Yeah, so it's what is called collaborative filtering. Collaborative filtering is when you do what? You don't care about the content. What you care about behavior. You care about the fact that the user is doing something with the documents. Okay? So these two approaches, they of course in practice are used together. It means that user, like the creator of the system, will benefit from both, from the content and from the behavior. But also, it means that there are like different ways of thinking about ranking. So you can rank based on the content, but also you can retrieve some information from the behavior. Very similar, I think, idea appeared more than half a century ago, related to the reputation of the source. So what if we add a new feature for ranking? Instead of, like, when there was no latent spaces, there were no vector representations, we have a list of something, for example, internet pages. And as I mentioned, we need to show user more relevant in the top, less relevant in the bottom. How should we rank if we don't know anything about content? If it's 1940s and you don't know how to embed a text into a vector space, how will you rank these texts? And the answer was that let's do something with the meta information about the data, not dig into the content of the data, but rather use meta information. And here we come to the world of Citation Matrix. In 1950s, there were two scientists. One is called Eugene Garfield, and second is Derek de Sola Price. Just don't care about these names, but you should know that there were such people who were considered as the fathers of Citation Matrix. Do you know what's Citation Matrix? No idea. Okay, so this is what we suffer from, like all the professors suffer from. So maybe 20 years ago, this thing didn't touch Russia, almost no way. But today, the efficiency, the quality of a researcher is measured by some numbers. So it's a very good thing to be able to measure a qualitative thing, like the quality of research, by quantitative metrics, by numbers. How to measure how quality is your professor is kind of a big task. And these guys, Garfield and de Sola Price, they approach this idea. Of course, at that time, they didn't approach the problem of a person, because there were a lot of researchers and the amount of data which we can process was not that big. But they started from the journals. And they said that we have this bunch of journals. Of course, we don't want to read them all. We don't want to go through the texts of the papers and somehow assess the quality. But what we can do, we can look at the last part of the paper. And this last part of the paper will say what? Reference. Okay? What do we cite? So what other researchers did the researcher cite in the research? And the idea was to explore only this part of the paper, not the content itself, but these citations, and to somehow build a ranking. That's what we are targeting, to build a ranking of journals. Okay? Because if you can do it for a paper, that's good, but the number of papers, even that time, was big, 1950s. And like thinking about such big numbers, if you don't have powerful computers, was painful. So, but the number of journals was not that big. So they could, for example, find their 400 journals and do some computations on them. And later, the big area, which is the part of bibliography, bibliometrics, sorry, emerged. And today, we can measure personal indices of people. Maybe you heard about H-index, Hirsch index. This is what today is kind of a status quo in the scientific world. Universities, of course, consider the professor as a person, But majority of universities will do what? They will put a threshold. They will say under this threshold, we will not even consider an application. So, for example, Sirius. Did you hear about Sirius in Sochi? Like another Innopolis, one more Innopolis. If you open their webpage, you will see that they hire assistant professors 5+, professors 10+. So no other criteria. They will go and consider your application if your Hirsch index is this. Okay? So Citation Matrix is now together a tool for management, for ministries, to somehow regulate the quality of research with numbers. And it's a big pain for professors because the way how different areas of science and the way how different people do research is very different. So yesterday, for example, I discussed the idea of books with our colleague, Oleg Kiselov. He said that I have a colleague, he's a mathematician, he writes books. And as book is not going through the peer review process, it's not in the world of Citation Matrix. So no one actually cites the book. Usually people read the book and they cite the paper which is referred here. But he introduced new things in the book and he doesn't get like any currency for it, so the currency of Citation Matrix. So you understand the idea. So there is a world of scientific publishing, and in this world, 70 years ago, some people introduced the idea that we can measure the quality of items, initially journals, even without looking inside the paper. Okay, 1975. Eugene Garfield introduced the thing, which is now still one of the important metrics in Citation Matrix. It's called impact factor, IF. So impact factor for this year, for a journal, will be computed like this. It will be the number of citations which this journal receives in this year. So it means that in the end of the year, we will observe all the body of publications and see how many other publications cited papers from this journal. Okay? And we divide it by the number of publications in 2020 and 2019. So it means that we say that usually like the peak of citation goes for the closest 2 years. That's kind of a good guess because researchers are forced to cite the freshest research. If you cite something from the 19th century, as I do, it's not saying that you like on the state of the art. You're doing some research, but this research is maybe outdated. But if you cite someone who published a year or 2 years ago, that means that you are like on the top of research. Okay, so this formula, impact factor, is still one of the important things of measuring the quality of journals. And they did a very good job. They explored some physical journals. And later, they got some criticism for this formula, but you understand that it's still working. So even with criticism, what kind of things are not perfect about this formula? So first of all, this is a relative scale. So there are no units. So there are some number of citations divided by publications. From year to year, absolute numbers of this formula can mean different things. Okay. Second, that implicitly, maybe it's not obvious from the formula, but there is some influence of the type of the paper. So the longer paper have difference from the shorter paper. For example, there is a type of paper called review. Review or sometimes survey. When in your paper, you explore the scientific area and you do a lot of studies and you cite a lot of papers. As well as physicists, they love to cite other papers and like everyone. And that's why this number of citations is boosted in this kind of world. So when people publish surveys, and reviews, they actually do what? They don't produce new knowledge, they aggregate someone's knowledge. So they create meta knowledge about the area itself and don't introduce new scientific approaches. And still, this increases the number of citations in the world, and it can influence the metric. And the last thing is that, of course, as I mentioned, like about the physicists, this is a very domain-specific thing. For example, mathematicians, they love to publish personally with no co-authors and usually don't cite anyone. So they say, let's say there is a well-known problem of 18th century of mathematics. Let's prove it. Okay, and no reference, of course, because like it's pure mathematics. And when you say about like physics, what happens? You do an experiment, you cite everyone who tried the same experiment, similar experiments, who contributed in this area, and so on. In computer science, it's kind of medium position, and any other area of science has its own way of behavior in terms of this metric. So it means that impact factor of the best biological journal and best computer science journal will be very different. Okay, it means that if you compare in absolute values, you will see strange observations here. Okay, so what can be done here? Like stating this criticism, in 1976, Pinsky and Narin, two researchers, tried to generalize the problem first and maybe find a solution. I cannot say that they found the solution, but they definitely generalized the problem. And they introduced the citation matrix. So citation matrix is just a general concept when you have C, I, J, and this means that the paper I has a citation on paper J. So J publishes some research, I references to this research. Okay, so this is like an inbound link. So J gets the citation, so it contributes to the H index of the professor who wrote this paper, and I creates a citation. So in Tech, you will have something like, do you know Tech? Tech? Okay, so it will be like cite J. Okay, nice. So, and what they said, let's slightly simplify this formula, because these types of objects, citations and publications, they are slightly different. So citations mean how many references do you have in the paper, and this is how many papers do you have. And they replaced publications with references, and they said the following. So let's, in the first iteration, say that so maybe I didn't mention it, but why do we need an impact factor? We need impact factor to do what? To rank journals, okay? The bigger is the better, the lower is worse. And some criticism in this area. So these rankings can only survive inside the domain, like itself in biology, itself in physics, but not mixed one. What they said, let's introduce another reputation scale. So let's do it slightly different way. So let's say that the reputation of journal I is what? Is a sum of citations journal I receives from other journals. So I hope people online can see it, but it's a sum for journal I gets from other journals divided by what? By how this journal cites others. So it's a sum of J, C, I, J. I remind you that citation goes like this. Okay? So what comes into I and what goes from the I. Very simple. So citation matrix, just the number of citations, and this is the reference, which is very similar. So these are still citations. Some of citations coming outside of, also coming inside the paper or journal or any other entity. And this is outgoing citations. Okay. So how can we express it in terms of metrics? So this is the matrix, for example, and the row. So if we fix I, means that this row says I cites everyone. And if we speak about column, so others cite I. Okay? So this is the matrix with some numbers. And the size of the matrix n by n, so number of papers, number of journals, they generalize, they don't actually state in the paper what they want to fix here. Just some number of items. Yeah? What is on the main diagonal? Zeros. So self-citations are not counted. Okay? And one more step left is that, yeah, so they did it, but they said, do you actually care in the same way about citations from good guys and about citations from not that good guys? So will you appreciate the recommendation letter from Professor Suchi or from me? So Professor Suchi is a big thing, and you will definitely request the recommendation letter from him. But otherwise, if he rejects, so you can go to me and ask me for this. But you understand that there is a value of item, and like citations of these items can have different weight. And they added one slight thing to the equation, and this thing was WK put here. So they said that we will weight incoming citations with a rank, with a known like reputation value. Okay, so you observe that W appears here, W appears here. So maybe I should use the same writing for W, not to confuse you. Let's say this W is a small curly W. Okay, nice. And what's next? The next thing is that this thing can be rewritten in a slightly different way. I hope you will see this one part, and then I will erase everything. So how can we write this formula in a slightly different way? Actually, very simple. So whenever you see a sum of multiplications, you can think about what? Dot product, yeah, wonderful. So you, woohoo, linear algebra. And if you write it like this, you will observe something like Wi is, sorry, Wi is C, and we have a column J. So it's more like Pythonic way of writing the, like it's a column of the matrix, divided by this number, sum of Cij, dot product W. So it iterates through W. Okay? And if you see this kind of interesting thing, so the ith element is the dot product of something. Again, so if an element is a dot product of something, what do you think about? So if an element of an object is a dot product of two other elements, most probably it's very similar to matrix multiplication. Okay? So, and knowing this definition, so of an element, so we do some norming of elements of our matrix, column-wise, we can rewrite it in a very simple way. W, here W, I will specifically note that this is a vector of values, so all from 0 to n, so from 1 to n, all n values of W, where you remember W is the reputation of an item, reputation of a journal, reputation of a paper, equals, let's call it C normed by W. Okay, very beautiful equation. In the paper, in the original paper, this CW is referred as, or C normed is referred as gamma transposed, but for me, it's like the derivative of citation matrix. So it's better not to introduce new letters if you can keep the old ones. And I will soon erase everything on the whiteboard, but I want to make a short comment here. Maybe you remember from the course of linear algebra. So how do we call elements of such an equation? If you have, let's call it C, okay, multiplied by vector W, and we have, again, the same vector W multiplied by some constant, let's call it lambda. So is it well-known concept for you? So wonderful. So we call lambda eigenvalue, and we call W eigenvector. Wonderful. So our problem here converges to very similar to this. So this one says what? We don't know the reputation for now. We don't know the values of reputation, but we know the metrics. See, so we can compute it. We know the inbound and outbound links, and we can try to compute it. So the only difference here is the absence of lambda. The authors of the paper, they introduced kind of a trick. They said that while solving this equation, we will restrict W to be weight normed. So they introduced some kind of a sum of weighted values of W and say it's equal to 1. So what they actually did, they said that we will bring this eigenvalue inside the matrix. So we will norm the matrix. Okay, so they didn't say this specifically, but they said that we will look for such a solution of this equation where lambda is exactly 1. So we will try to find such a solution, and they have some, I would say, reasons to believe that this is true, and we will cover these reasons a little bit later, but they didn't specifically specify them. So why do they think that they will be able to find the solution with lambda equal 1? So they introduced this kind of thing, and they called it eigenvalue, eigenvector problem. Actually, this is kind of just an eigenvector problem, but they formulated this exactly for a reputation search. So we need to find an eigenvector, which is just a list of ranks, list of reputations of our items. Nice. And also, they, in some form in the paper, 1976, remember, discussed the method, which is known as a power method. Do you know power method? Power iteration method. Oh, wait. Okay, so I will erase and show you this method. So remember 1976, citation matrix. We're somewhere here, and the major takeaways from this speech is that we can form a matrix, fill it with adjacency, so who cites whom, and only having these metrics, only having these information, we can rank the elements by reputation. So there is some essence of reputation, which is, you remember, we defined it very naturally. So we like the incoming citations of good guys more than incoming citations of other guys. And from this, we formed the equation, and we got the reputation list. And the power method, or power iteration method, power iteration method, it's a very simple idea. So what do we know about this equation? So let's work in terms of the same letters. So lambda omega equals C omega. So what it means in terms of the geometrical properties of eigenvectors and eigenvalues. Eigenvector is not disturbed by the matrix. So if we assume that this matrix is a transformation matrix, it's like an evolution. Yeah, so it's you have a system, and you evolve a system using this operator. This operator doesn't touch this vector much. So it only can scale it by lambda. This is the only effect which we can observe. Okay? It's a geometrical idea. Yeah. So it means that if we multiply it by lambda again, it will be the same as just applying our operator multiple times, 2 times. Okay? So, and if we can continue, we will still be able to write this equation. So we evolve our system multiple times, and this is the same as just scale our vector by some constant. And we know this constant. Okay, and the essence of power iteration method is that if this matrix doesn't touch the eigenvector, it touches other vectors. Okay, if you have another vector, it do what? It somehow changes it. And the idea of method that it should evolve a vector if you apply it multiple times until it converges to the place where it doesn't change. Okay, so the idea that if you have a linear operator, it will try to convert a random vector into an eigenvector. So there's a very good demo on Wikipedia, like a very short animation. When you have a random vector, and if you apply an operator multiple times, in some iterations, it will convert into an eigenvector by applying this matrix. So the idea of the method is that if you apply this operator to a random vector multiple times, it will be the same if you apply this operator to an eigenvector. So this of course, this random vector should be normed. So it should be divided by the sum of elements. But this is the beautiful observation. So if you apply more and more times, then you will be able to converge to this value. And this is one of the beautiful methods of computing eigenvectors. So without knowing the eigenvector, only having the transformation matrix, so our matrix of citations, you just multiply a random vector multiple times by this matrix, and you get what? You get an eigenvector. Pa-dam! Beautiful mathematics. Okay, and the authors of the paper stated that they converged this process, so the vector stopped changing in 64 iterations. And what's beautiful about 64? So about 64, beautiful is the following thing. If you do C in power 64, so you just need this matrix. In this matrix, C in power 64, multiplied by a random vector. So you can write what? You can write C squared, 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 6 times. Okay? And that means that you need only 6 matrix multiplications to get these beautiful matrix. So instead of doing 64 multiplications, you do 6. You can compute the evolution matrix, which looks far into the future. Okay, and then you multiply it just by a random vector, and you observe eigenvector here. Okay, and this is what the authors of the paper added in the computation part. So they stated the problem and they said how they computed. Yeah. Not all matrices. I would say that that's a good question. So for the sparse matrix, I would say that I think that if you still keep in mind that this is a graph, the connection, I'm not sure about exact definitions, but I remember that there is a strict connection between the graphs and having a determinant. And this can be only 2 reasons why we don't have a determinant. First, there are multiple connected components. And second, there is like a loop, the cycle. Okay, so if they don't observe such things in their graph, then yes, But they didn't introduce it like this. They just introduced the computational method. I think that in terms of numerical methods, sometimes you can sacrifice the exactness of mathematical method if it still works and gives you some numbers. Of course, yes, the diagonalizable matrix should be, but they never actually stated in the paper. They said that it works. Okay, so two things which we will base our future discussion on. So we have half a lecture passed, and actually half of the material covered. Not half, third of material, no, half. Nice. And now we will move 22 years forward. Go 1976, and 22 years forward, the year when the company called Google appeared. 2 years before, in 1996, two unknown scholars from Berkeley, from where they were, Sergey Brin and Larry Page, they wrote their master thesis about ranking. So this question was discussed, as you see, multiple times, but they tried to apply it to a particular new event, the internet. There was no internet in 1976. There was internet in 1996. Okay, and they said that let's define a Markov process, so the one which you define by probabilities, of crawling the internet. Let's introduce a random surfer, not a superhero, but just an imaginary person who travels the internet. And we want to express the authority, the reputation of an item in the internet by the likelihood that this random surfer will stop at this page during random crawling. Okay? So you randomly crawl the internet, and at one moment you stop somewhere. The more likely you will stop here, the bigger is your reputation, the more paths lead to this place. Like a philosophy page in Wikipedia, for example. If you click the links randomly in Wikipedia, you will one day end in the philosophy page. And they said, let's our model work like this. Let's say we have what is called PageRank, okay, of an item A. And at the next iteration, so it's a recursive formula, T+1, we will express it as a weighted sum. Here, it will be PageRank of X, and X is taken from the set X from V, so X is a vertex of the graph of like it's a page, yeah. And we have an edge from X to V, so it's also to X to A, so we call it A, X A, from edges. So what it means? It means there exists an edge which goes from X into A. So we will compute the rank of our page through ranks of our neighbors who cite us, who point to us. And we will norm it by our degree of X. So do you know our degree? So the edges going outside from the element. So if you draw it as a graph, so let's imagine you have one, two, three. So 1, 3, 2. So imagine a graph like this. The our degree of 1, 2, and 3 will be all 1. Okay, so only one citation. And the out degree of 4 is 3. So it cites all 3 pages. And the idea of a PageRank is kind of an idea of diffusion in physics. So you pass what you own to your neighbors in equal parts. So the PageRank of X, let's call this X, will be transferred in equal shares to all the neighbors. Okay? So you have some reputation, and you share your reputation with your peers. And your peers accept this reputation. So you have the constant amount of reputation in the network. I know all of you, so I will give all my reputation to you in equal parts. And you will receive this reputation in this part, and also you'll receive from all your peers. So of course, this is like an iterative process, and as this is very similar to physics, it should at one moment converge to a stable state. Yeah. So this is, you see, this is a, I forgot here, of course, t, so known value. So it's an recursive formula. So we expect it to converge. Okay. So the end of the algorithm is PageRank. Let's do it at moment t plus 1 minus PageRank at moment t less than some epsilon, some small value. So we will run this process multiple times, iterate, and wait until it converges. What's strange with this formula? I think the strange is that if we remember the formula W equals the sum of CW divided by C, by J, by K, Ki, Wk, we will see that actually this is what? Citation. Oh, so sorry, this is W, is reputation here, okay? C here can be what? Either 0 or some value. So it can act as a delta function, which contributes here. So which edges we take. And this norming is actually what? It's an out degree. So how many outcoming degrees are here? So sounds like the formula is the same. Yeah, so at least in essence. So what's new in PageRank? That it is a new method. And this new consists of 2 introductions. Okay. So of course, this formula is in the first approximation. On Wikipedia, you will find like a simple version of PageRank. What's new? Actually, the first thing which was introduced in their paper is called the Dampen Factor. Very simple idea. The idea is the same as you observed in the page about, in the article about pfound. You remember that when we spoke about pfound metric, we said that there's a model of a user who is lazy and can be tired. At one moment, you will just, oh, come on, I want to stop surfing, I want to go and have some food. Okay, and they introduced this probability of continuation with very well-known number. You remember? 0.85. Yeah, so the probability of continuation is 0.85. And let's say D equals 0.85. And actually, when the other groups of researchers were doing their research, they tried to improve this number, somehow compute the better value, and actually they convert to something close to 0.95. So how they use it? They say a very simple thing. Each page can be the place where you stop without any reason. You don't continue following the links. You stop here, okay? With probability of 1 minus D. And they rewrote the formula in improved version. So T plus 1 of A is what? Is this probability of stopping with no reason, 1 minus D divided by N, so where N is the number of documents, plus the same sum, okay? Sum of X, here we have PageRank of X divided by out degree of X, okay? So just one simple thing, they smoothed the thing. And what they could achieve with this, they achieved a very interesting situation. None of the pages has 0 PageRank anymore. So even if you have a PageRank which you have no in degrees, so you just a random node, you will still get this random part here. And the second, if you are a lonely person, if you don't cite anyone, if you don't want to continue the search, so if a user clicks, and situates in some page which has no outlinks, so there's no way to pass the PageRank to your peers. They introduced the idea of these kind of nodes are called sinks in the network. Sink. You remember sink and source from the algorithms course. Source when the stream goes outside, sink it where it finishes. And they said that let's imagine that the random surfer is on such a page. What should this random surfer do? It opens a bookmark page and clicks a random link. So they say that we will add a behavior in which if you're stuck, you will restart from the random page. Okay? So it means that the probability, so the PageRank is distributed among all the pages equally. So you just take whatever you have and spread it through all the other peers. Of course, this is a very small value because you have like millions of pages and billions of pages. So it doesn't significantly influence their PageRank, but it allows to PageRank not to be accumulated in a single node. So now you have a very well-connected network, no sinks, no nodes which are just orphans. And what's interesting, did I introduce it? No, I did not introduce it. And also, yeah, so I will rewrite the formula in the original way. So first we will replace this sum with a matrix multiplication, but before we need to cook this matrix. Okay, how we will cook the matrix. So first we will start with adjacency matrix, and it is like the opposite direction. So J cites I. Okay, then we norm, so we divide by column. So we divide each element by column. So Sij is Aij divided by column. And the last thing, we will add this. If we have a row, so we have such a node which has no outgoing links, we will set them all into 1 divided by n. Okay? So these 2 steps. And in Wikipedia page called PageRank, this matrix after 2 iterations is called M, and I will then refer to this as M. In Google Metrics page in Wikipedia, this is referred as S. So these are interchangeable names. So I will stick to M because it's in the page of the original page of PageRank. Nice. So now we need to rewrite this with respect to Dampen Factor and processing sinks. How it looks like? It looks like this. PR. So now it will be the vector. So I will denote it like this. In moment t plus 1 is what? Now, as it's a vector, we need to add this term to any element of the vector. How can we do it? They propose to introduce a vector called 1, which is a column vector of ones. Okay, so just this one is 1, 1, 1, 1, n times. Okay, so this one, big one, bold one is this kind of vector. Okay, and this term. And this term appears to be just D M P R T. Okay? Nice. What can we do with this formula? First of all, we can take into consideration the fact that we are not just introducing an iterative process. We introduce an iterative process which should converge. Yeah. So at one moment, these two things should become equal. Okay, as in previous time. So this is an iterative process which should converge. That means that we can do what? With some not very big strictness of mathematics, we can remove these terms. Okay, nice. And if we are linear algebra students, we can do what? We can say we have x, we have some known things. So this is well-known constant, 1 minus d divided by n. This is Dampen Factor, 0.85. This matrix we just computed it in an iterative process. Adjacency matrix, norming, introducing 1 divided by n. And the good student of linear algebra course will say what? He or she will say it is PR minus dm PR equals 1 minus d divided by n. We are close. So what we can do, we can put the multipliers here. We can say I minus this. Okay, we have a matrix which we can compute. We have unknown vector. And we have a constant which we know. And what's the last step left? We'll multiply it both parts by this inverse. Okay? So I can keep some space. So maybe it's slightly confusing, but the idea is that we took this formula, we rewrote it in a matrix form, very simple form, and it appears that it's just a set of linear equations. So let's solve it. And if we look at here, if we multiply it by this inverse, we will get what? PageRank equals 1 minus d divided by n 1. And of course, I forgot a big bracket. I minus dm. So wow, almost done. So we know how to compute a PageRank with the only problem. What do you think about this matrix, which is the number of pages in internet by the number of pages in internet inverse? This computational process can take some decades, centuries, maybe millions of years, who knows? And otherwise, we can use a trick. Which kind of trick? Let's look at this formula again. And let's look at this strange one. What we know about PageRank? PageRank is flooding equally through the neighbors. So if you sum up all the out degrees, they will sum up into the PageRank, yeah, back. And this is a trick which is used in computations. Very simple trick. We can say that E, and here E is the square matrix of just ones. Okay, this kind of matrix, multiplied by PageRank at any iteration, we don't care, is equal to this one. Oh, and you lost the professor. Okay, so this trick allows us to replace this one with this multiplication. So let's do it. So PageRank is just a Dampen Factor E by PageRank plus dm by PageRank. Sounds like we have a beautiful part here. We have PageRank in both segments, okay? And the last thing we need to write here is what? PageRank equals 1 minus d divided by n e plus dm multiplied by PageRank. So we get rid of time things, so these indices on the top, and we just converged to the form of a problem which we already saw. Yeah, so we saw that PageRank equals matrix, huge matrix, multiplied by PageRank. PageRank is a vector, okay? And this matrix is called Google matrix. Just the name of the matrix. So the matrix, if you form it in this process, fill the square matrix with these constants and plus Dampen factor multiplied by adjacency matrix. So this simple procedure give you a thing called Google matrix. And now you understand one important thing. You know how to solve such problem. Yeah? 20 years before, some people showed how to solve this problem. The only thing here which is more strict in terms of mathematics is that the properties of these metrics are slightly better than of just some adjacency metrics. These properties are, this matrix is stochastic. What do you know what's stochastic matrix? It's a matrix where either column or the row sums into one. Okay, because it describes a Markov process. Markov process means that if you stand here, you can go in some direction with some probability. Okay, and these probabilities should sum up into one. And if you remember EM algorithm, we didn't cover it. Okay, so no problem. So stochastic metrics. Stochastic metrics. So there is right stochastic and left stochastic metrics depending on what should sum up into one, either rows or columns. So right stochastic matrix is when it's ij equals 1, and when it's I equals 1. So this row sums into 1, this column sums into 1. And there are few beautiful properties of stochastic metrics. One is that the dominating eigenvalue of such metrics is 1. So lambda 1 equals to 1. Okay? And the other interesting thing is that you remember we did a small change. We introduced a Dampen factor, which allowed any node to have at least some PageRank here. And that's why our matrix is full of positive values, so no zeros. Okay? And this means what? This is the positive matrix. Okay, and there is a theorem. It's called Perron-Frobenius theorem. Perron-Frobenius, which allows to all positive matrices and some matrices which are consisting of zeros and positive values. Like, and these metrics fall into this like whole variety of opportunities for Perron-Frobenius theorem. It states that it has lambda 1 which is greater than 0 always for such matrices. So matrices with positive values have positive first eigenvalue, and what is important, the eigenvector of such matrix, the first, consists of consists of all positive elements. This is good for us. So altogether, we know that this lambda 1 is greater than 0, and it's equal to 1 because it's stochastic and positive matrix. Okay, and the second thing is that the eigenvalues of this matrix, they are all positive. So it guarantees us very simple thing, that the result of PageRank algorithm will converge into positive values of ranks. So there will be no negative values here. So these values will be positive. Okay, so from Perron-Frobenius theorem, that's an obvious outcome. So E one, which we are looking for, is vector of all positive values. The last step, I think. Yeah, so we define the Google metrics. So I will draw a bold blue box around. Just a short break. I will write Evgeny Sirchudinov that he can come. And that's it. I think that this one part is finalizing the problem itself. So you can use, and actually Google said that they used PageRank to this statement of the problem, and they used power iteration method, and they could converge in 52 iterations. So 52 matrix multiplication by itself led to convergence. So the 52 iterations, and they have the matrix which doesn't change after time. Okay, and this was the result of 96. Later, few things appeared. Of course, this kind of algorithm can be a subject of manipulations. And you maybe remember the times when there were companies who sold links. So they were like, for example, some farm which create a website, and they posted links for you, which could do what? Which could transfer you PageRank from them for money. Okay, so they have their own PageRank. They merged with some value, and while updating, Google should see that there was a reputation of the page, some neutral, and then they spread this reputation to other pages, and you can buy this reputation for money. And this is how you could fool the algorithm. Other thing is it's not clear how you should behave with advertisement. So advertisement is what appears at your page, and again, you can start setting up the presentation. I will switch on if it works, I don't know. What.comp. Okay, so you don't know how to behave with this advertisement. And in 2005, together with community and the new standards of HTML, there was forced the application of HTML attribute nofollow. If you know that in HTML you have a href something, and also you can add nofollow, meaning that if this link is seen by a robot who crawls the internet, the robot should not proceed with this link. Okay, and that means that the Google forced people to use this for advertisement. Because advertisement is some kind of randomly appearing link, which should not be considered as the link in the graph. And there was a change, which was a subject of manipulation. For some reason, I don't know what was the business reason, these links, nofollow links, were not counted in out degree. So there was an out degree somewhere here on the whiteboard. They were not counted as outgoing links, but they were counted for incoming. So there was something that, for some reason, pages which have nofollow aggregate PageRank of others, but they don't give the whole PageRank to their peers. So if you have half of nofollow links, half of PageRank will remain at your node. And this was a strange behavior which was exploited and was called a PageRank sculpting. So the companies could manipulate nofollow links to aggregate PageRank on their side, and then Google will use this value to do what? To do a ranking in the standing of documents. Okay? So no content-based, just links and nofollow manipulation. Just 2 minutes. And one thing left here is that, of course, PageRank is an initial phase. So Google started with this algorithm. They evolved it for multiple years, I think like 13, maybe more years. Some changes then appeared. Of course, now we rank based on the content, but during that time, few ideas very similar to PageRank appeared and helped to do some positive changes in the world. So for example, there was an algorithm which is called PageRank. So PageRank. And the only difference of this algorithm was to take the Google metrics, the adjacency metrics, and invert all the links. Instead of I cite you, I say you cite me. And this allowed them to aggregate the information and to rank the nodes based on their ability to be a hub. So they introduced the term hub. Hub means how many places can you visit starting from here. So like imagine this is the airport or like something where you start traveling from. So the big hub should allow you to travel everywhere. The next thing that the idea of authorities and hubs. So authorities are from PageRank, hubs from PageRank, was slightly improved by Kleinberg, the person who did a great research in small world graphs. So he is a very good researcher in graphs in general. And he introduced the hits algorithm, which computed both authority and hub property of each node. So it's kind of two-dimensional algorithm, which could place your page in two-dimensional space and saying how good this node in reputation and how good this node in passing the reputation to others. And also some other methods. For example, trust rank. The algorithm, which is very similar to PageRank with the only difference. So why should we believe algorithms if we can believe humans? And they started with the seed values of rank given by humans. So the humans ranked some pages of internet, and then they started the algorithm. Okay, so there are multiple different modifications, which were I would say, built upon PageRank, because PageRank was the first implementation for very large-scale matrices. So before this, we could not work with these many items. So you remember that we started with journals. The number of journals is some hundreds of journals. Now we work with internet pages, which are billions of them. And still, by having some sparse representations, we can compute these Google metrics. And this is what we expect you to do in contest today. And to get ranking results by power iteration method. I think that even if you didn't understand any part of the lecture or some part of the lecture, my intention here was to do a very simple thing. We speak about internet, very applied thing. We speak about services internet, very applied thing. We started with modeling this with graphs. So we started with graphs. We said that the graph is here. We introduced some algorithm based on graphs. And then we just used another mathematics of linear algebra, to express the same idea. So we rewrote the problem based on graphs in a problem based on matrices. And then we said that here is a problem, here is a computational task, how to find an eigenvalues of the matrix which we know. Keeping in mind that the matrix is essentially big. And next comes what? Computation, algorithms, which say we know how to compute such a big thing. Okay, instead of doing an inverse of the matrix, let's do power iteration method, which can be efficiently coded in C, C++, Python, whatever. And that's I think, the beautiful place where practice, graph theory, linear algebra, and algorithms meet together just on a single whiteboard. Okay? So thank you very much for attention. Online visitors, if there are still some, thank you very much for attention.